Okay, so we're ready to move on to the next lecture. In this lecture video, we will be building up all of the mathematical tools to understand how a transmission line or how a pair of conductors can become a carry medium for electrical waves with voltages and currents, particularly in the form of waves. All right, so this lecture is divided up into three pieces. The first will dive into the circuit model of transmission lines, and we will build up the basic formulations for voltages and currents within this transmission line model. And then we will use that to derive something called the wave equation, which will describe a moving wave, precisely the way we expect. And finally, we'll talk about different types of transmission lines and how they vary from each other. And so starting off with the transmission line circuit model. Right now, in the last lecture, I first introduced it, but just to remind you of what's going on here, we're imagining that a transmission line consists of a lot of very small segments pieced together. And in reality, those segments are basically ridiculously small or infinitesimally small. But let's say that each segment has a distance of delta x between them. Okay, and so we daisy chain all of these little segments to make a full transmission line. And these segments are basically going to have two key components, right? There's an inductor and a capacitor, right? There's also resistances that are going to give us some loss, but we're mostly going to ignore that. But inductors and capacitors are going to be important. So the inductor is going to be responsible for converting voltage into current. The basic equation for how an inductor works is here. The equation basically tells you that if you would like to change the current in an inductor, you first have to put the voltage across it, and then you've got to wait for that current to ramp up gradually. The speed with which it ramps up is defined by the inductance L. If L is really big, then di dt must be really small, and so your current is going to ramp up very slowly. All right, capacitor is essentially the same, but we just reverse everything. The capacitor is going to convert currents into voltage. And so for a capacitor, if you'd like to change its voltage, you have to first run a current through it and then wait for the voltage to charge up. Okay, now if we put an inductor and capacitor together, you can see the beginnings of at least an oscillation, because I can take voltage and turn it into a current. The current can turn back into a voltage. That's the inductor and capacitor working together. And then I can get a cycle of voltage to current, current to voltage, voltage to current, and back around again. But that's an oscillation. That's not a moving wave. In order to get a moving wave, there's something that's missing here. We have to introduce spatial variations into this somehow. And so that is where we're going to start to introduce something called the telegrapher's equation. And the telegrapher's equation will be a straightforward result of the circuit model. So I'm going to draw the circuit model here, and we'll have a line right here, a branch. I'm going to put an inductor. We'll have a resistor. Now I'm going to draw a capacitor and another resistor right here. I'm going to draw this like that. And I'm going to draw the same branch again, just to remind us that this is repeating over and over again. And so here's the resistor. All right, so this inductor value is going to be L. But let's define distances here for a second. Let's say that this branch has length of delta x, right? That's the length of this one branch. So the inductance value that we've got in this little branch is L times delta x. Remember, L is the inductance per unit length, so we have to multiply by the distance in order to get the actual total inductance, right? And the same for the resistance. We have an R times delta x. Here we have a capacitance times delta x, and we have an admittance G times delta x. Okay, good. So let's talk about voltages, right? Let's define symbols for voltages. Let's say we take the voltage and measure it right here, and we're going to call that the voltage defined at point Z and also at time t. All right? At the same time, let's say we measure the voltage right here. That is going to be the voltage defined at location Z plus delta Z at time t. All right, so now we can define the voltage in two different places. Of course, they might be different from each other, which is why we have to do that. But we're not done with just voltage. We also have to have some current, so let's define that as well. The current in this branch right here, we're going to call that I at location Z and time t. And in this branch, we will have I at location Z plus delta Z and time t. All right, good. So we're all set to go. What we would like to do is find relationships for how the voltage and currents in the next branch, Z plus delta t, relate to the voltage and currents in the previous branch. So let's try to write down these relationships, just given our understanding of circuit model. Yeah. Slide this back a little bit. So first, we want to figure out how V of Z plus delta t relates to V at Z. All right, so V of Z plus delta Z at time t, we can probably say something about the difference between them, right? We can apply basically Kirchhoff's voltage law to tell us that we can say something about V of Z plus delta t minus V of Z at time t, right? Let's say that there's no voltage across the inductor and there's no voltage across the resistor. Right? If that's the case, we know that these are equal to each other, and so this must be equal to 0. However, if there is current running through these two, through this branch, this I of ZT, it's running through this resistor and it's running through this capacitor, this inductor. And so we actually know that there's a non-zero difference between the two. So this is going to be I at Z at times t times R times delta X. This will define the voltage drop across the resistor, right, defined in this way. And there's also going to be a voltage across the inductor, right? Let's just write that as VL. All right, so plus VL. I'm going to have to put a minus sign right here because the positive current is going to force the voltage in this next branch, Z plus delta Z, to be smaller. So I'm going to put a negative sign right there. Okay, good. So given that, we now have a relationship between V at one branch further down the transmission line to what the voltage is at the original location. Let's try to do the same thing for current. All right, so we have an I at Z plus delta Z time t minus I at ZT. For that, we're going to basically put our attention right here at this corner, and we're going to apply Kirchhoff's current law, which tells us that we can't have net current flowing around. We're not going to disappear anything. And so this we can write in a sort of similar fashion, that this is equal to the voltage at Z plus delta Z times the admittance G times delta Z. Right? Remember, the admittance G is 1 over R, so this is a current right here. This branch right here is a current, plus the current that's in the capacitor. Right? So there is a current right here that's in this capacitor, and I'm going to define that as this I little c. All right. Let me just remind you a couple of things here. This branch right here, this I R delta Z, this is the voltage across R. And this branch right here is the current along G, right along that admittance, that leakage resistor. All right, so Kirchhoff's voltage law, Kirchhoff's current law are in place. But we got this VL and IC right here that are kind of sitting there and are very annoying. Luckily, there's something we can do to actually replace them. All right, let me get a different color for that. How about orange? All right, we also know that VL equals L times delta Z times DI dt. And we know that I across the capacitor equals C times delta C times the derivative of voltage with respect to time. So we can substitute these two things in here, right? The VL and the IC are going to substitute in there. And then we'll have a couple of equations, and we can put those together to form something called the telegrapher's equation. I'm not going to go through the details, but if you substitute these in, rearrange, and then shrink delta Z to be incredibly small, you end up with derivatives, right? Instead of delta Z's, you get DTs or DZs. And so you're going to end up with a pair of telegrapher's equations that look like this. dV, let me go back to black. All right, so these are called the telegrapher's equation. If you want the details for how we get from these two equations here to the telegraphers, take a look at the notes. But the telegrapher's equations look like the following. dV dz, the derivative of voltage with respect to Z, equals minus R times the current minus L, the inductance per unit length, times di dt. And the second one is going to look very similar, except we're going to swap the V's and the I's. This is a moving wave. That should not be a surprise. The derivative of current with respect to time equals minus G times the voltage minus C times dV dt. These are called the telegrapher's equations, number 1 and number 2. All right. You can start to see that this is very close to what we defined as a wave in the last lecture. When we said we have to have two quantities. The spatial derivative of one gives you the time derivative of the other, and the time derivative of the first one gives you the spatial derivative of the other one. Right? We can start to see that, and to simplify, let's say that this is an ideal transmission line. Okay, so we don't have any measurable resistance along the transmission line, and we don't have any measurable leakage between the two transmission lines, which means that R equals G equals 0 for an ideal, what we would call lossless case. Okay, so that allows us to remove a couple of these terms, and we've got dV dz equals minus L times di dt, and di dz equals minus C times dV dt. This is exactly our mathematical definition of a wave that we derived earlier. Now, let me prove, I'm not going to prove to you mathematically how you can get waves from this. There's some details in the notes, and we're about to get into the details in the next nugget. But let's start out with this notion. These are called the telegrapher's equations. We know that they define a wave. We've already talked about that, and we're able to sort of, just from inspection of a circuit line model, derive these two equations. And so that tells us right away we should have a moving wave here. In the next module, we're going to talk a little bit more about how we can show that this is a wave and how that wave works.